Welcome, everyone, and thank you for attending today's Parasoft presentation on streamlining ISO 26262 and 21434 compliance with automated testing. My name is Ricardo Camacho, and I'm the Director of Software Safety and Security Compliance at Parasoft, and I'm accompanied by Miroslav Zielinski, Director of Product Management for our C and C++ testing solutions. He's a brilliant mind and a good friend. How about testing your microphone by giving us a hi, Mirek?
Hello, everybody.
You sound loud and clear. Thanks, Mirek. On the agenda, I'm going to put the backdrop of standards, regulations, safety, and security into context and then provide a glimpse into ISO 26262 and ISO 21434. These two standards relate to each other in the development and verification of software. In fact, ISO 21434 references ISO 26262, and I'll show where and how these two standards intertwine. I'll then quickly discuss continuous testing, which continues to grow as a best practice by the major automotive manufacturers in satisfying compliance to safety and security standards ISO 26262 and ISO 21434. And then I'll pass it over to Merrick, where he will demonstrate these verifications solutions. Following that, we'll do our live Q&A. Okay, before we get started, let's go through some housekeeping. First, everybody's microphone has been muted. However, if you have questions, please enter them into the questions dialog box. You can do this at any time. Also, this presentation is being recorded and will be made available shortly after the webinar. All right, let's get started. The automotive industry has a lot of standards to ensure the safety of the software, and we have standards like ISO 21434, but you may also have European regulation WP29 R155 on vehicle cybersecurity. We don't have the time to go into details on R155, but I want to quickly get across that addressing security takes place at different phases of the software development lifecycle, as well as in the stages of development, deployment, maintaining, and sunsetting the vehicle. For example, you have ADAS calibration tools, ECU programming equipment, key programming devices, and other advanced diagnostics tools that interface with a vehicle's electronic systems. These tools can provide access to sensitive vehicle data and settings, making them a target for misuse. So these security vulnerabilities need to be identified and remediated. It's part of your threat analysis and risk assessment. This security analysis trickles down through the software development process, and ISO 21434 defines what should be done at the embedded software level to address software security. And much of it mimics how you address safety, which, if you've been in the automotive industry for some time, you are very familiar with. So let me quickly touch on ISO 26262. The latest ISO 26262 2018 is subdivided into 12 parts. The standard has been evolving since its first edition, released back in 2011, but I'm only going to skim over parts 4 and 6. Part 4 is the beginning of product development at the system level, which has various phases. At a high level, they are comprised of requirements management, design, implementation, and testing. These phases have been partitioned into two domains, Part 5 for development of hardware and Part 6 for development of software. Our focus is software, so let's dive and skim through Part 6. You can see the lighter gray V watermark. The left-hand side of the V encapsulates the requirements decomposition, design, and implementation phases. On the right side of the V, sections 6.9, 6.10, and 11 represent the testing or verification validation of the software. This includes static analysis, unit testing, structural code coverage, requirements, traceability, and more than that. This is a graphical V diagram from the standard showing parts 4 and 6, but notice the horizontal lines across the V that separates the different phases of development and verification. You can clearly see that you have different abstraction levels of testing. System testing at the top right of the V integration testing in the middle right, and unit testing at the bottom right. The V development process is heavily used, but don't confuse it with a development methodology like the waterfall or an agile methodology. The V is a recommended process, it's not a development methodology. Okay, let's start connecting this to the security standard ISO 21434. Requirement 0505 states that organizations shall identify related disciplines and determine if and how cybersecurity will be integrated into existing processes. Since you all have been using ISO 26262 for safety and probably are very familiar with it, you can integrate security into your development process very quickly. Automotive organizations have systems engineers doing safety, now working closely with security engineers, defining both safety and security requirements, performing hazard analysis for safety and threat analysis for security, plus the risk assessment. So basically, HERA and TERA. This is the V model represented in the ISO 21434 standard. The graphic is a bit coarse, but you have development on the left and verification on the right with different levels of abstraction. This means you need to isolate and test your security functions. For example, unit test your encryption function, your decryption function, and for integration testing, test higher level functionality or security requirements like testing your boot process to check that digital signatures of the bootloader, operating system, and application software have not been tampered with. And for system level security testing, make sure that communication protocols to ensure confidentiality, integrity, and authenticity of data exchange between vehicle components and external entities is secure and functions as expected. So you need to perform unit integration and system testing to satisfy ISO 21434, just like you already have to do for ISO 26262. So let's take a look at some of these test requirements. Integration and verification requirements in Section 10 specify methods for verification, such as requirements based testing. So you need to link to requirements and create test cases to test those security requirements. You will also have to put in place your coding guidelines and perform static analysis, which I recommend a combination of MISRA and CERT. You will also need to perform dynamic analysis, which means unit testing, integration testing, system testing, and other types of testing. There are also methods recommended for deriving test cases, such as boundary values, like min, max. There's also error guessing based on experience. And of course, there are other methods as well. Requirement 10-11 calls for test coverage using code coverage metrics. When you create test cases to verify security requirements, you want to make sure that the security test case fully exercises the security functionality. For example, if you have a numerous path and complex if statement with multiple conditions and decisions, you want to make sure that every path is tested. Using code coverage, specifically MCDC coverage, will ensure that you have created every test case needed to fully test the code that is meant to mitigate your security vulnerability. This is referred to as test coverage to determine sufficiency of your test activities. Therefore, because statement coverage does not analyze and cover complex branches, it is not adequate for security test coverage as stated in the standard. Since statement branch and MCDC is recommended for safety by ISO 26262, you can accomplish both code coverage and test coverage at the same time for safety and security. Now, this is just an infographic putting it all as a visual. You have the V model showing development and verification for both safety and security in parallel through the software development lifecycle. Our C++ testing solutions focus on the bolded testing methods you see listed here, like static analysis all the way down to requirements traceability. But Parasoft also offers testing solutions like API testing, penetration testing, service virtualization, and more. So contact us if you are interested in trying out these other testing solutions. Also, Parasoft CC++ test is tube certified, as well as our other product called DTP for reporting and analytics. Now, one other very important topic that I want to mention is deployment of verification or testing methods to automate compliance to ISO 26262 and ISO 21434. We have noticed that automotive manufacturers have been and continue to adopt a continuous integration type of development workflow. Within the CI pipelines and development ecosystems, you see open source testing frameworks like Google Test, coding standards like MISRA, CERT, a vast collection of compilers, debuggers, targets, IDEs, document reporting solutions, tools like Git, GitHub, Jenkins, and let's not forget requirements management tools like Jama, Codebeamer, Jira, and we can continue to name tools. The key point that I want to make is that we have noticed that many automotive development organizations have been and continue to adopt a continuous integration type of development workflow. They mentioned that they have been able to better predict the delivery of software to better accommodate changes in requirements and design. But one of their biggest tells is a drop in QA problem reports and customer tickets. This also has equated to lower cost in testing and development. And they have noticed an increase in product quality and time to market. Because of these realizations, they are now focused on automation at scale and being able to deploy CI/CD pipelines for large, complex projects. The automotive industry is looking to further optimize the pipeline with light command line tools. As I mentioned before, we see a lot of use of VS Code, GitHub, and so forth. And actually, frameworks like Google Test for unit testing and even homegrown frameworks. Many automotive embedded development teams love using testing frameworks like Google Test, CPP Test, Boost Test, and CPP Unit. Frameworks like Google Test are easy to use. It has a straightforward syntax for writing and maintaining tests. It offers a wide range of assertion macros, which help in verifying the expected behavior of your code under different scenarios or conditions. A key advantage of Google Test is that it integrates well with popular build systems like CMake, making it easy to incorporate testing into your build process and CI pipeline. It's also designed to be cross platform so you can test on various operating systems. And because it's widely used, there's an active community where you can find lots of resources, tutorials, and discussions. So Parasoft wants you to take advantage of Google Test and other similar testing frameworks for unit integration and system testing, but we want you to get more value from this effort by enriching them. For example, you can take a testing framework like Google Test and enhance it by adding Parasoft's structural code coverage, requirements traceability, and report generation on top of it. Now, these additional capabilities simplify and expedite compliance to ISO 26262 for safety and ISO 21434 for security. It saves in time to test, time to market, labor costs. You will experience a high reduction in issues and produce safe and secure and reliable components. So let's get to the fun part and see this in action. Okay, handing it off to you, Merrick.
Thank you, Ricardo. In our demo setup, we will use a popular combination of technologies. GitHub is our CI platform. Developers use VS Code for coding and Google Test for unit testing. Our toolchain is fully Dockerized, and it includes CMake, Ninja, GCC compiler, and of course CC++ test CT. The use of containers ensure ease of infrastructure instantiation and consistency between developers' desktops and CI. Our development process is based on the CI workflow. In our demonstration, we will see an example of the workflow with testing for compliance. Our focus will be on unit testing and code coverage, but this kind of workflows almost always include static analysis and coding standards compliance. In our demo, we will go through the following sequence. We will start working on a new code in a dedicated feature branch. The code will be developed, according to requirements defined in Jira. Implementation will be tested locally at the developer's desktop using Google Test and the containerized toolchain. In the next step, the developer will create a pull request. The pull request will trigger a pipeline with an automated quality and compliance gate, which includes more extensive testing than developers can perform on their desktops. The pull request will fail in our demonstration due to insufficient MCDC coverage. Pipeline's execution reports will be published on GitHub pages, and after a quick analysis of the report published on GitHub pages, the developer will download pipeline results to local VS Code and use extended reporting features to save time developing missing test cases. After fixing all issues, the developer will push the code back to GitHub and the pipeline will be re-executed. The quality and compliance gate will open this time and the developer will merge the code with the main branch. The merge operation will trigger another pipeline that monitors the state of the stable stream. The results of this pipeline will be sent to Parasoft DTP, a web-based reporting system that aggregates the testing data, generates compliance reports, and visualizes testing results with graphs and trends. Let's switch now to our demonstration environment. Our demo project is based on a popular open source library for inter-process communication. In our design, we plan to use it in the autonomous driving system. Our project is hosted in GitHub and team uses a modern CI-based development workflow with containerized toolchain and automated CI quality gates. For our code, we need ISO 26262 AZD compliance. So far in the early stage, project was developed with limited attention to standards compliance. This frequently happens when internal company components developed without standards compliance or open source modules are mixed into a safety critical system. In our situation, we plan to certify adopted open source module which was internally extended with new functionalities. So far, when working on the project, developers used Google Test for unit testing, but the process has not been systematic. Testing was not traced to requirements, and code coverage was monitored only for line metric, which is not sufficient for functional safety. The investment in creating Google test cases is already significant, so we want to use them for certification and save our team's effort on rewriting these tests to a proprietary framework. For our next compliance milestone, we have two goals. We want to start monitoring statement and MCDC code coverage for the newly created code, and we want to start tracing relevant tests to requirements. With Parasoft CC++ Test CT, integrating code coverage into project builds is easy. There are dedicated integration packages for build systems such as CMake or Bazel. The tool is also very easy for containerization. To integrate the tool for our demo project, we need one small insertion in the CMake list file and the corresponding configuration file. With this change, our build targets are extended with code coverage monitoring, and we can move on to implementing new features. So let's say our task is implementing the emplace method for a vector class. We do have a set of low-level requirements for this functionality. As a developer, I've analyzed the specification and implemented the first version of the emplace method. I've also added the first couple of unit test cases. Please note that my test cases are correlated with requirements via dedicated properties injected into test cases. This correlation establishes a test to requirement link that enables CC++ Test CT to generate requirements traceability reports mandated by all safety standards. Now, I'm interested in whether my tests pass and the code coverage level for my newly implemented code. Let me build the project, run new tests, and generate code coverage reports. As you can see, the code was built and tests were executed. As a part of the build process, C++ test.ct generated code coverage reports. CT generates reports in multiple formats, including raw text, machine processing friendly JSON, and HTML. For developers, the VS Code extension is probably the most convenient way to analyze the results. Let's enable line coverage and look at the new code we just added. As we can see, we do have some code coverage, but our basic tests examined only a part of the implementation. We need to add more test cases. We can derive additional test cases by requirements analysis. Let's add a few more tests, ensuring they are linked to appropriate requirements, and execute them. We expect coverage for the mplace method to increase. And indeed, it seems we now have 100% line code coverage. We are now ready to push the new code to the repository and create a pull request. My pull request triggered the automated pipeline. The pipeline goes through several stages, including code coverage quality gates. Let's take a look at our pipeline definition file while it executes. What we are looking at now is the YAML file that defines a GitHub workflow. Workflows contains jobs and steps that are executed on runners. C++ test.ct Lite command line interface and build system integration packages make it very easy to integrate into workflows. Here, the code coverage tool is injected into the CMake build. Build integration extends existing targets with code coverage and adds new targets for report generation. Our project default target includes building Google tests. Here we execute binaries with unit tests, and here we invoke reporting targets added by the C++ test.ct CMake extension. Once the report is generated, it's published to the GitHub pages so that the team can easily access it. Below are quality gates for coverage metrics. Our current requirements for the quality gates are 100% statement and 90% MCDC code coverage for the new code. The values are set with helper variables. Let's go back to our pull request and see the pipeline results. Our pipeline has failed. It seems we have a problem with MCDC coverage. Our line coverage quality gate passed, but the MCDC quality gate has failed. We simply did not achieve expected 90% of MCDC coverage for the new code. To understand the gaps, we can review the HTML report published on GitHub. The report contains complete results for all metrics, including details for MCDC or simple condition coverage metrics. The results summary table has configurable thresholds to indicate with colors results that may require attention, and covered code constructs are marked with highlights. Different types of results decorations, simplify quick reviews, and deeper dives required for a complete understanding. HTML report published to GitHub or GitLab pages may be a convenient way for a team to get an overview of the coverage levels after pipeline execution. For fixing the code, adding new test cases, and improving coverage, it may be more convenient for developers to view results using the VS Code extension. The C++ Test CT VS Code extension integrates with GitHub and enables downloading pipeline results to the local VS Code and viewing results without executing code locally, which is a huge time saver. We can now analyze why our MCDC coverage quality gate failed. Let's see MCDC results for the method we are implementing. We have 3 decisions in the method. For 2 of them, we have achieved 100% MCDC code coverage. However, we still don't have the complete MCDC coverage for the first decision. Let's take a closer look. C++ Test CT provides extended MCDC coverage reporting that helps understand coverage gaps. Diagnosing missing coverage can be a time-consuming task, especially for MCDC. This extended reporting provides easy-to-understand visualization of MCDC coverage and instructions how to add minimal number of test cases to achieve coverage goals. In our situation, we have 3 conditions in the decision. The second and third conditions are already covered according to MCDC requirements. We still don't have the coverage for the first condition. Here we have a list of test vectors that were executed. Table includes information about the values that conditions were evaluated to and the outcome of the entire decision. Below, we have the information about missing test vectors. A great value is that the tool computes the minimal set of the test vectors required for the complete coverage, helping developers to be more productive. In our case, we need a test vector to evaluate the first condition as true. It means we need a test case that tries to emplace an object at the position exceeding current capacity. Let's add this test case. In general, depending on the situation, different actions may be required to eliminate the coverage gaps, including changes in implementation, modification of requirements, and the addition of missing tests. In our case, the code was correctly implemented, following requirements, but the developer forgot to add a test case for a specific scenario. The problem was detected thanks to the C++ Test CT-based quality gate. Let's make sure our new test case is correlated with appropriate requirement, and now we are ready to push the code again. Let's add a comment. Alright, this operation triggered a pipeline for our pull request. Let's give it a minute to finish. Alright, it seems our coverage quality gate passed, and we are now ready to merge the code into master. For the master branch, we have a dedicated pipeline verifying integrated code. That's a different pipeline than the one executed for pull requests. This pipeline executes an extensive set of tests and monitors the code coverage for the entire project. Our merge operation triggered this pipeline. The results of this pipeline represent the current status of our stable branch. Our pipeline sends these results to Parasoft DTP, the reporting platform. Parasoft DTP aggregates inputs from different types of testing and presents results in graphs, trends, and compliance reports. With these widgets, I can monitor my progress in various compliance aspects, including the progress with the code coverage. I can also check the progress with requirements implementation and testing. With this widget here, I get information about the number of requirements already covered with test cases and those that are not and require attention. This information allows me to react if my progress with compliance goals, including code coverage, is too slow. Unlike the point reports published to GitHub pages, which are useful for assessing the health of recent commits, DTP provides more in-depth analysis, including history and trends, and enables decisions regarding resource allocation and development process optimization. This kind of insight is essential for any persona involved in the safety, security, or quality process management. And this is the end of our demonstration. Let's recap. We went through a typical development workflow. A new functionality was coded in the dedicated branch. Implementation and testing were driven by requirements stored in Jira. For the new code, a pull request was created, which failed due to insufficient MCDC coverage. Developer used VS Code for accessing pipeline's results to understand the problem and fix it. Corrected code was pushed to repository. The second pipeline was successful and the pull request was merged. Push to the stable branch triggered another pipeline. The pipeline results were sent to DTP for trends and compliance reports analysis. In our demonstration, we focus only on unit testing and code coverage, but static analysis with MISRA or other coding standard could be implemented in the same way with Parasoft tools. In our demo, we extended the typical development workflow with compliance testing without reinventing the pipelines or changing existing development patterns. Integration with the existing CMake build was trivial thanks to a dedicated integration package. Developers didn't need to learn a new framework or rewrite existing Google test cases. All these aspects of software testing influence the certification cost. The overall cost also includes toolchain maintenance, which may be significant in the case of open source tools. Any problems in the toolchain may affect certification deadlines if we don't have a vendor behind that can react to a bug. The complete cost and effort analysis is not possible without knowing project-specific details. It is possible, however, to indicate where significant differences are. The important factors include cost of acquiring the toolchain. Here, open source tools look better than commercial products. However, when we add the maintenance cost, the situation is different because of the risk related to not having a vendor behind the tool. With open source tools, the qualification effort tends to be significant and may distract the team from their core activities. Commercial products are typically pre-certified, which reduces the overhead on the qualification. Another factor is the cost of integrating the toolchain into automated workflows. Here, solutions that depend on IDE or heavy GUI interfaces, like old-style unit testing tools, are definitely more expensive to integrate. And then we have cost components that scale with the size of the team and project. Commercial products based on proprietary testing frameworks require training for the entire team, which consumes a lot of time and causes distraction. Open source tools and frameworks are known by developers and typically do not require training. The cost of creating new test cases depends on the framework and team's proficiency in using the framework. Some of the commercial solutions use GUI-based test cases editors and proprietary scripts for defining test cases. These kind of tools sometimes enable test creation without coding skills, but when used by developers are visibly slower. Dev teams make the fastest progress when using popular open source frameworks such as GTest or commercial tools that utilize GTest. Teams that consider using a proprietary unit testing framework must also consider the cost of migrating already created Google test cases to the new framework. The cost here is proportional to the number of test cases and in many cases can be prohibitive. With Parasoft C++ Test CT, this cost does not exist. And finally, we have a cost of achieving coverage goals. With open source toolchains, teams get only a basic coverage reports without any additional hints how to create test cases that achieve higher coverage. This is especially relevant for MCDC coverage, which is challenging for non-trivial code. C++ Test CT provide here a great value by extending reports with additional hints that highly simplify missing test cases creation, reducing the overall cost of achieving coverage goals. As we mentioned earlier, the complete cost analysis depend on project-specific aspects, but the factors we listed here are among the most important. And this concludes our presentation. Ricardo, passing to you for a quick summary.
Thank you, Merrick. Okay, let's do a quick summary. That was a fantastic demonstration of integrating continuous testing into the development pipeline. Merrick demonstrated how easy it was to add Parasoft's C++ Test CT's code coverage and requirements traceability onto Google Test, as well as reporting. C++ Test CT is one of our new products, and by the way, the CT suffix stands for continuous testing. Thank you again, Merrick. Now, go to the next slide here. The barcode that you actually see will take you to our products page for our C and C++ software testing solutions. There you can learn more about our product offerings, the testing capabilities and static analysis, unit testing, code coverage, and quite a lot more. You can also download the data sheets of our products, take a simulated tour of our products, watch short introductory videos, and request a trial or demo of C++ Test or C++ Test CT. Also, if you have any questions after the presentation, you can email us at info@parasoft.com. We're also on LinkedIn, Twitter, Facebook, and YouTube. Follow us or watch our extensive collection of videos that we have. Okay, so we're going to open it up for Q&A. We actually have several questions. Our first question is CPP core guidelines coding standard good for security and 21434 compliance?
Okay, so I'll take it. CPP core guidelines, it's a good coding standard. However, it lacks a security focus. So for any organizations developing with C++, we recommend using CERT C++ and MISRA C++ in addition to CPP core guidelines, if that's your standard of choice. It is a common practice, however, among organizations to create a superset of coding guidelines by selecting the most appropriate guidelines from the popular standards, such as MISRA, CERT, or the core guidelines. So probably that's the answer.
Okay. Our next question, I think, Merrick, for you, are there any specific requirements for unit testing stemming from ISO 21434?
As far as my knowledge of this standard is considered, there are no detailed or special recommendations for unit testing stemming from 21344. However, to follow the spirit of the standard, one recommendation could be to create tests that exercise the behavior of your functions and methods when given unexpected inputs. This is what hackers will try to do at various levels of your system user interface, and your low-level code implementation shall be ready to deal with this kind of unexpected inputs.
Okay. One other question. What application was the C++ code developed for? I think that's the demo the person's asking. It is just one of our examples that uses one of popular libraries for used out there in automotive. Which is the ICE Oryx. Anyways, hopefully I answered that question for you. If not, please clarify. Our next question is, how much additional effort does ISO 21434 add over ISO 26262? That's a good, interesting question. Now, so the effort depends. So 21434 calls for, again, unit testing, static analysis, code coverage, or test coverage. So these are things that you're already applying when you perform ISO 26262. So there's not a lot of effort there. However, performing to ISO 21434 also involves doing your threat analysis, and that in itself is a whole different methodology, ideology that you need to perform. That you need to perform your threat analysis and risk assessment. So there is a lot of effort there, but of course, your systems engineers and security engineers will work together to develop all those requirements. In fact, that leads to the next question, which asks, what is the difference between HERA and TERA? So HERA is hierarchical, not hierarchical, hazard analysis, risk assessment, and TERA is threat analysis and risk assessment. As I've seen little variations on versions of this, but they're distinct methodologies used for different purposes in risk assessment. One is HERA is focused on safety, and systems engineers will use a technique like fault tree analysis to help them perform risk assessment and reliability analysis. By modeling the paths leading to system failure, they can then engineer solutions that remediate these failures, ensuring that the system, if it ever fails, it fails as safely as possible. And then TERA focuses on security. So security engineers will use security standards or techniques defined by frameworks that provide structured approaches and methodologies and best practices to ensure a comprehensive and effective security risk management process. And some of these frameworks are, for example, NIST SP 800, or you might have heard of ISO 31000. And there are more frameworks out there, and there's techniques like SWOT and tools like OWASP, Threat Dragon, or Stride. So basically look at these frameworks and these methodologies, and then you can decide which ones you want to adopt to flush out all of your vulnerabilities and perform your security analysis and risk assessment. Okay, we have another question. I have a project with several hundreds of Google test cases. Is there anything I need to do with these existing test cases to start using Parasoft for code coverage and requirements testing?
So in general, there are no special changes or modifications required to existing Google tests to run them through our product. The modification may be required only if you want to deploy requirements-based unit testing. In such case, you will need to annotate existing test cases with the information which requirement they test. This is an easy and non-intrusive modification, of course, assuming your team understands which tests are relevant to which requirements.
Mm-hmm. Thank you. We have just one more question. Is there an evaluation available for Parasoft? And absolutely. You can go to our website. In fact, you can go to our C++ testing solutions product page, and you'll see our options there for different products. And you can also click on the Try Parasoft button, and you can also request a demo and evaluate the product. Let me see here. Okay, so there was just this one more question that just came up. I guess we'll take, even though we're way over time, so this will be the last question. What are your thoughts on good tool management according to ISO 21434? Requirement 514 Of course, well, Parasoft tools for unit testing, for code coverage, requirements traceability. I recommend that. You want to also use other tools like OWASP to help you out. And I really like the NIST 800-30 for security as a framework and methodology for you to use. Okay, folks, please, if you have any questions after this demo's over, email us at info@parasoft.com. Mirek, thank you again. Very excellent demonstration there of our solutions. And we have these every month, and that concludes our presentation. Thank you, folks. Bye-bye.